Hello, Rouse. This is lesson 6.1 on arithmetic sequence. Arithmetic, not arithmetic. It's an adjective, not a noun. It's also the first day of Unit 6 on discrete functions. So I'm going to spend a little bit of time here talking about some stuff that the printed lesson doesn't address that we would normally have conversations about in class. So let's use the first movie theater example. The movie theater has 21 seats in the first row, 24 seats in the second row, 27 seats in the third row, and so on. And the first thing that I want to do is get a function here. Let's figure out where there is a function. Let's see if we can declare our variables. Let's see if we can explain why it has to be a function. And then we'll talk about what makes it a discrete function. So these values that you're seeing in this list, this is another way of defining what a sequence is. It's just an ordered list of numbers. It could be finite in size or it could be infinite in size. We're going to use these values as our outputs. And normally we would say, oh, we'll let that be the number of seats. So maybe we would use S. In this unit, we'll be referring to these as terms of a sequence. And I'm not that consistent about using uppercase T or lowercase t. Instead of, well, you know what? Yeah, let's go back to let me just use C for number of chairs. Trust me on this one. And then my input, the input in these sequences is a little bit tricky because it's kind of hidden. Your input actually represents the term number. So this right here is how many seats there are in the first row. This is how many seats there are in the second row. This is how many seats there are in the third row. There's nothing really like 1 or 2 or 3-ness about this other than its position here. So call this the row number right there. And you can have C of n represent the number of chairs. Represent the number of chairs in row n. Whoops, row n. Okay. So, a couple of conversations here. This must be a function. Let me explain it using specific variables for any possible row number, meaning there is no row number 1.5 or 1.6 or -3. There is only one, and maybe I should specify, because if you ask me, are there 9 seats in row 1? An obnoxious person would say yes. If you clarify and say, are there at least 9 seats in row 1, we would say yes. Is there a total of 21 seats or chairs? Maybe I should let this represent the total number of chairs in row n. There is only going to be one total number of chairs. So it must be a function. The restriction on domain. Suggest a reasonable domain for this function, and you'll see that we're talking about the set of all row numbers n. There's probably going to be some sort of maximum. I don't know how many rows there are in a movie theater, depends on the theater. None of this is what makes this a discrete function. It's this right here. The fact that n has to be an element of the natural number system. We did this all the way back at the start of Unit 2 when we talked about suggesting some reasonable domains for functions. In fact, a couple of the functions, a lot of the exponential functions that we looked at in this course have been discrete functions. If you're talking about the number of gels that you put in front of a light or the number of times that you photocopy a piece of paper, your input is going to be counted. Input is counted. It jumps from one value to another. And basically it is a member of the natural numbers. Now, when you're dealing with discrete functions, there's usually a consequence that your outputs are also members of maybe integers or whole numbers or natural numbers. but that's not necessarily the case, and it's not what makes the relationship a discrete function. Okay? So the notation here. Normally, when we're dealing with a discrete function, we want to make it absolutely clear that we're dealing with a discrete function. So we'll call these outputs just terms in a sequence. So this right here is term number 3. Notice that the input of 3 now becomes visible. I could say that term 3 is 27. And the 3 here isn't a 3 in the same way that, say, the next term of 30 has a 3 in it. It's an index or a position or an input. It's the row number. This is the number of seats. So let's scratch that out and call this T sub n. And it's the one case where even in applications, we probably won't be using variables that are related to our quantity. We'll tend to use either uppercase T or lowercase t to represent the term number. Okay. Now, I want you to, hopefully you have already had a run through the lesson and you've taken a look at arithmetic sequences. Let me just point out that, I guess I'll go through it quickly here. Notice that in this specific sequence, the difference between term 2 and term 1 is 24 minus 21, which is 3. The difference between term 3 and term 2, that's 27 minus 24, that's 3. We call that our common difference. We call that value D. We say it's 3. And if your sequence has a common difference, that's what makes the sequence arithmetic. Okay. For any sequence, we call the first term lowercase a. And this means that for an arithmetic sequence, your first term is a, your second term is a plus d, your third term is a plus 2d. So that right there, that's term 1, that's term 2, that's term 3. Just illustrating that, once again, we don't have to have much memorization here. There's a couple of new symbols that we're looking at, new letters. But the formula for the general term of an arithmetic sequence, notice that the third term has 2 additions of d. And this should make sense. You haven't gone forward 3 times. You start at the first term and you go forward 2 times. The second term has only 1 multiple of d. The first term has 0 multiples of d. So this means that by the time you get to the nth term, the general term or term number n, you are going to have 1a plus n minus 1 multiples of d. And there's your first formula. Okay. All right. Let's try out example 3. Go through example 1 and example 2 on your own and let me know if you're having any problems. In example 3, it says that the 7th term of an arithmetic sequence is 53 and the 11th term is 97. It says determine the 100th term. So a key part of this unit is that efficient solutions should take about as long if you have 1,000,000 terms as if you have only a dozen terms. So you do not want to develop trial and error type approaches in this unit. I'm hoping to avoid multiple choice quizzes in this unit because I don't want you to just sort of use trial and error. You're going to have to show your work and send in your own solutions. So you could probably figure this question out with trial and error. You could probably do a couple of operations and figure this question out. But I expect to see the directions on a question like this that say use a system to solve. Okay. We have been solving linear systems in grade 9. We did that graphically. And then in grade 10, we solved algebraic systems. It's been a while since we've had to solve one, though. We might have seen one all the way back in quadratics. Okay, so both of these, sorry, it did say that it was an arithmetic sequence as well. That's really important because that means that I know that I can use this formula. This formula has 1, 2, 3, 4 unknowns in it. 2 of those unknowns are variables and 2 of those unknowns are parameters. Luckily, I'm given 2 hints, almost like 2 points on a line. If I substitute this information in, then I get 53 the 7th term is going to equal the first term plus 7 minus 1 times d. And let me just tidy that up over here on the right-hand side to 53 equals a plus 6d. Notice I can't use this to solve for a and d. There's an infinite number of possibilities. But I also know that 97, the 11th term, is going to equal the first term plus 11 minus 1 times d. It's a really good idea. Doing 11 minus 1 is a very simple operation, but I'm sure students would be confused if I just wrote 97 equals a plus 10 times d. So show your reader where these numbers come from. Here is a linear system. Linear systems can be solved through elimination or substitution. I'm going to suggest that you stick to elimination. It's useful later in this unit, and it continues to be useful in other courses. Substitution, not so flexible. I am going to choose to eliminate a by announcing what I'm doing. I'll do equation 2 minus equation 1. So if I have 97 minus 53, that's going to be what, 44? And a minus a will be 0 a's, 10d minus 6d will be 4d's. Then I just have a linear equation that I solve by isolation. That tells me my common difference. Now this is where some students will say, couldn't I just do 97 minus 53 and divide that by 11 minus 7? Well, that's exactly what I've done. The difference is that I'm showing why that works. Sometimes students think that there's like a slope formula here. These discrete functions don't really have slopes because they're not continuous relationships. Okay? Practice using a system. Now that I know my common difference, I can substitute into equation 1 or into equation 2 to solve for a. It shouldn't matter which one I use. I'm going to put it into 1 because my numbers are a little bit smaller. I might regret that in a second when I end up with some negatives. I'm going to have 53 minus 66. You know what? I can't avoid the negatives. I'll get a negative value anyway I do this. And what's that? Negative 13. So now that I have what I can build into a general term, that the nth term of this sequence is given by negative 13 plus n minus 1 times 11. I can substitute in the number 100. And I don't need to write out. I've seen grade 11 students solve a problem like this by just listing the numbers all the way up to 100. This is what I mean by efficient solutions. I could make this 1000 and it doesn't make the question any harder for a student who knows what they're doing. Okay. If you're using a strategy that you say, oh, I just need 10 more minutes to list out all these values, or I need a bigger piece of paper, you're probably using a wrong strategy. Sometimes in our textbook, they ask us to simplify the general term. That only really happens for arithmetic sequences. But it is interesting to sort of point out the relationship here between sequences, arithmetic sequences, and linear equations. This is going to start to look like an equation in the format y equals mx plus b. With a slope of 11, this means every single time we go up by one term, the term number goes up by 11. That's my common difference. I never realized it was the same as that index there. But the dependent intercept in our application, this would be the 0th term, the term that comes before the first term. For our movie theater example, so you're in the front row and there's 21 seats. That means that in the row in front of you, in row 0, there would be 18 seats. There is no row 0. The reason why we don't just use a linear equation here is because in discrete functions, n begins at 1. So this negative 24 doesn't really mean much to us. Okay. But this is called the simplified general form. And it is a little bit easier to use. If I want to evaluate what t of 100 is, it's all ready for me to just substitute in. T of 100 is going to be 11 times 100 minus 24. That'll be 1100 minus 24. 11 times 100 minus 24. It'll be 1076. Okay. We'll be using systems at other points throughout the unit. I'll continue to review them. You'll find some examples where you're given clues like this in your homework. Practice it by using a system. That's the skill you want to develop, not just finding the answer. Okay.